Hi, my name is Cameron Fenn, and I am presenting this paper that is joint work with Samir Undavia, improving external validity of machine learning, reduced form, and structural macroeconomic models using panel data. And so I guess to motivate why our question is important, why is improving external validity important, a fundamental problem in macroeconomics is essentially we have data that starts from 1947 and ends in 2020, but it's only quarterly, so this is only, something like 250 to 300 data points. As a result, we can't use, more complex models. We're stuck, if we're using reduced form framework, we're stuck using a VAR or AR models. If we're going to do a structural model, we have to use some sort of, domain name expertise from, microeconomics in this form of sort of DSGE, heterogeneous agent structural models. And the problem with that is essentially, these models have been developed because we just don't have that much data, right? This, as an example, this COVID recession, we've never had anything like this in the history of our data set, right? So we really can't, we're really predicting out of sample. Likewise, the Great Recession even has not much that's similar to that, especially because we had the sort of, an L-shaped recession where you had a large decrease and then very slow growth recover. There is almost nothing like this except the Great Depression, which is even further back, and we just don't have good data on that. And so what we're going to do, propose to fix this, this really important problem in macro, this dearth of data problem, is we're simply going to pool together many different countries, right? So we're going to, even if we're forecasting US GDP, our objective is to simply use sort of Japanese data, French data, and pool all that data together, form a panel, and use the sort of panel to sort of forecast US GDP. Why might this work? For example, the SARS epidemic may look something like this COVID epidemic in terms of both the huge recession followed by the very fast bounce back as well. And perhaps the Japanese sort of Asian debt crisis can shed some light on the Great Recession and the sort of path dependence and the slower growth growing out of the recession, right? There has been other work that has done this on a sort of ad hoc basis, so there are papers, I don't know off the top of my head, that use Japanese recession data, especially during the debt crisis, to model Great Recession dynamics. But we're just predicting for a general forecasting problem, right? If you're a central bank and you want to sort of figure out, predict what interest rates will be like, and even if you're a central bank and you want to use a structural model, right? We are proposing that when you use structural models, you should also use you should also have this pooled data rather than just using sort of one country's data, like only US data to forecast US GDP. And so, this is a sort of answer to our question. We're going to use a country-by-country panel data, and we're going to pool the data together to form, a larger data set, right? So instead of having 300 US time steps to estimate our model on, we'll have something like 3,000 to 5,000 country time steps that we can estimate these new model, our traditional economic models on, and it will improve them across the board, essentially. So, let me just go through this slide. We advocate fixing this dearth of data problem by using a panel of 49 other countries plus US data. This is our solution to this sort of dearth of data problem. What this solution offers, it improves external validity of in a wide variety of circumstances. We improve external validity as measured by forecasting performance in the reduced form, so the AR and VAR models. We improve it in the structural model, so we use the Smets-Vauters DSGE models and improves the performance there. We also improve the performance in machine learning models. We use recurrent neural network and a AutoML set of models. And again, across the boards, across all these different models, we show improvement, right? And another just sort of suggestion is, the reduced form models, the linear models have the least number of parameters. Their improvement is the least significant. It's still something like 13%. The root mean squared error improves by roughly 13% from the baseline of using just a single country. Likewise, when we improve our structural models, the improvement is about 25%. And this is partially because our structural model has more parameters. De Smet-Vaudreuil models has roughly 40 parameters, as opposed to the a VAR model, which has maybe 10 to 16 parameters, and an AR which has much fewer. And then I should note that this improvement is sort of from a higher base. The structural models performs less. The baseline structural models perform less well than sort of the reduced form models. And then we use our machine learning models, and our improvement on the RNN, which is the only sort of stationary model, the AutoML model. I don't mean stationary in a time series sense, but I mean a stationary in the sense the AutoML chooses different models depending on the circumstance. It's essentially a model search algorithm, and so for the less data abundant regime, it's going to choose different models than the more data abundant regime. But the RNN, we estimate the RNN on both the data, the dearth of data regime, so the just US data, and then also on the world panel. And the RNN improves root mean squared error. Improvement is about 23%, which is sort of less than the structural model, but the RNN comes from a higher base. There is more improvement, and the RNN actually outperforms, as well as our AutoML outperforms all other models along almost all horizons that we test. And so it's sort of a new sort of state of the art using this panel approach, or the pooling approach. So that's the first thing. We show external validity across a wide variety of circumstances improvements. It allows us to draw more fundamental conclusions. We demonstrate that this augmented data makes reduced form and structural models more policy invariant. And so we'll run a test which essentially, typically all our forecasts are time step out of sample, right? So we don't have any training data from Q4 2008 to Q1 2020. And that is all in our test set, and we test the performance of our model. However, we can actually test generalization even further by being not only time step out of sample, but also country out of sample. So what we'll do is we'll train our model on 49 other countries, but not the US, and we will test on US GDP forecasting performance in this out of sample test set as well. And then we show that even in this framework where we don't have any US data, the model learns to generalize to the US as a country, and we get a sort of, we get both structural and reduced form models that are sort of more able to generalize and more sort of policy invariant and learn a sort of general policy for countries, even if they haven't seen US data. And they outperform models that have been trained only on US data. And of course, they don't outperform models that have been trained on all data, including US data, oftentimes, but they still already are an improvement over models just trained on US data. And then the third thing is our machine learning models, right? We show that this procedure opens up the use of more flexible nonparametric models, like our 18,000 parameter recurrent neural network that outperforms all baselines in this data-rich regime. Likewise with our AutoML model. So the data in our baseline models. We evaluate the performance of our model via GDP forecasting. We're just choosing GDP as one variable. We're going to go through a variety of models, and so we just like to keep it simple and use and test on one economic factor, right? We in preliminary tests we sort of determined that GDP lags, consumption lags, and employment lags were the most predictive components for GDP forecasting, and so we use a panel of 50 different developed and some rich developing countries to test the sort of assumption that GDP, consumption, and employment, we use that to forecast GDP growth. We'll use a variety of models. Again, our AR2 is a reduced form of our VAR1. We have a VAR4 that we use at times. they all use this reduced form model. Our recurrent neural network and the AutoML also takes into account only these three variables: GDP, consumption, and unemployment. Data sources, as you can see below, the test set I've mentioned already. And then, so for the other models, we have the Smets-Wouters model and the factor model. So AR2, VAR1, recurrent neural network, and AutoML all use only these three covariates to predict GDP. Smets-Wouters model, of course, is a structural model, so it takes in something like 11 covariates. GDP, I think consumption. I don't think unemployment is in there, but there are sort of 9 others other than GDP and consumption. And then the factor model, again, uses, 248 different covariates, including GDP, consumption, and unemployment. The factor model, unlike the rest of these models, we actually only test the factor model as a baseline model. We lack the resources or the data ability to essentially get a panel data across many different countries for our factor model. So our factor model is only US relevant. It only takes in US data. We don't do the same sort of tests that we do for all the other models where we compare trained on US only versus the world. The factor model only is a US only model. However, we use the factor model to do, as a sort of baseline comparison in our recurrent neural network and our AutoML outperforms this factor model. Even though the factor model has 248 covariates, although it doesn't have any sort of cross-sectional dimension, cross-sectional country dimension. So the baseline models, again, this is just a description of the models, sort of vaguely. If you want, you could just read through this. I'm not really going to go over this. You can just, if you're non-familiar with the model, you can sort of just take these models sort of as black boxes, as sort of like, effective forecasting models in economics. But I think it helps to sort of understand these models to have a more detailed description of exactly what the pooling helps and what it doesn't. And I think the lesson essentially is from our paper that using this pooled, augmented, panel data or pooled panel data, all these models improve by a significant amount. So almost any model you can think of improves when you go from data from a single country to data from all countries, or as many countries as you can get a hands on. So the first thing we'd start out is reduced form models. So the reduced form models have the least number of parameters, but performance is there's still an improved performance, right? So here is our graph. We've basically interacted horizons by the model type. So we have two models, AR2 and a VAR1, and we interact the horizon. So this is 1 period ahead forecast. This is 2 period ahead forecast. And again, you can see that across almost all models and all horizons, we get significant improvement in root mean squared forecast error. So this would be, again, on our same test set that I talked about before in the US. So both the world data and the US data are used to forecast US GDP. This makes it sort of apples to apples comparison. And so other than the first horizon, all the horizons show improvement from the in a root mean squared error sense. The improvement is roughly 12%. So from this baseline, a 12% reduction, right? The stars indicate significance, Diebold, Mariano, significance, and the stars, are at the 1% level for 3 stars, which are not here, 5% level for the 2 stars, and 10% level for a single star. Right, and as you can see, across almost all horizons, you get very consistent outperformance when using this pooled data. So again, this graph makes it seem like this pooled data is obvious, but I just like to point out that the improvement is not obvious. There's a literature in machine learning on negative transfer, and the basic idea is, maybe French data is not representative of US GDP, right? So the new country that you add is more biased in terms of forecasting. It will decrease variance because you have more data, but it is biased, and it is unclear a priori whether the bias outweighs the variance. And of course, since the literature hasn't really focused on using this pooled data to do forecasting. You focus on single country forecasting. Obviously it wasn't clear to practitioners. Otherwise, people would have, the literature would have really moved to this. And I mean, there have been, individual papers that have probably, dealt with this pooling data in an ad hoc basis. But again, as far as what the Fed is doing, what policy is doing, most of the models are being trained on single country data. And yeah, so that is the first, problem with this. I will get into a second problem of using pooled data and why the pooled data overcomes that. But the second issue will be more of a structural argument, and I'll discuss that in our structural model section. And so again, the other thing you might discuss is a sort of, there is a sort of path dependence in the U.S., and so U.S. GDP has declined since Q4 2008. In a sort of, this is a sort of, dealing with, productivity slowdowns and stuff like that. And you may make an argument that, the world data has already slowed down among developed countries, and this is just artificially, this biases the predictions downward, and the U.S. happens to also have that downward prediction, right? But this forecasting performance is not constrained only to the U.S. So what we do here is we take each of these models, the AR2, the VAR1, and the VAR4. What we do is we have the two different tests, local data test and the world data test. So with local data tests, we take each of our 50 countries in our panel, and for each of our 50 countries, we train a single model, so a French model to predict GDP, a South African model to predict GDP. That's the local data approach. And for each country, we predict GDP on our test set for each country out of sample, of course. And then we average the root mean squared errors across all the countries. So this is like 50 different models predicting GDP and then averaging them across all countries. And then we display each horizon. The world data, we take a single model, right? One model trained on all the data. So all the data is pooled together, and then we forecast all 50 countries jointly in the sense that we use a single model to forecast GDP for all different countries. And as you can see, this performance is not constrained only to the US. The improvement in root mean squared error is significant and large across, a large number of countries. Another thing to note here, just to, sort of feed into our story is, the more parameters you have, you do really poorly here because I think there's not enough data, and so this VAR4 is very much overfit. But, with this pooled data, you actually get increased performance from the AR2, right? So the AR2 to the VAR1 has an increase in performance, and the VAR1 to the VAR4, actually, it's not in these significant figures, but actually the VAR4 actually does slightly better than the VAR1. However, you are sort of getting this sort of, it seems like there's a sort of barrier, right? It's almost like there's sort of an irreducible error. These linear models cannot do any better than just sort of this sort of irreducible error. The VAR4 does do better than the VAR1. It just, you can't see in the significant digits. But this irreducible error, there's almost like a linear irreducible error, and I'll show you when you use even more flexible nonparametric models, and even to some extent when you use the DSGE model, you are able to break this barrier a little bit. And the idea is sort of like, we shouldn't assume that linear models are well specified just because they have been good forecasters in the sort of the lack of data regime, right? When you have more flexible models, you actually can break this, this forecasting barrier, and it's not like this is as good as you can get. Again, this just explains this cross-country interpretation as I explained before. If you want, I have these slides in my on my website, and so that way you can follow along without this presentation. Again, so this is the second test, and so I've tested, the forecasting performance not constrained to the US. This test, the blue bar and the red bar here in each of these tests is the same as the blue and the red bars here, right? So these two bars are still the same. Again, you still have this sort of interaction. And the third bar is sort of out of sample data, right? What this means is essentially you have essentially what we do, as I talked about in the sort of introduction slide, is this out of sample data I use. I'm forecasting US GDP, right? This root mean squared errors for US GDP. And so what I'm going to do is, instead of training on every single country, so all 50 countries plus the US, I'm going to train on all 49 countries except I'm going to not train on the US. So this is forecasting both out of sample time step-wise and out of sample country-wise. And again, this illustrates that this sort of pooling the data actually makes these models better generalizers, right? This model, the yellow data, has never seen US data at all, and yet it can forecast US GDP pretty effectively, even though it has not seen any US data. And this illustrates, the other thing this illustrates is, the pooled data is more similar across space than it is, more similar across space than it is different, right? And it suggests that, you don't even need US data to outperform models trained on US data, right? So this is, the blue line is the models trained on US data, and across, I think, almost all horizons, the out-of-sample data does better than models trained only on US data. So models that have no US data in them perform better across all horizons and all models than models that are trained only on US data. And I think that's an important takeaway to illustrate that this sort of pooling procedure also makes models better generalizers. And again, when we talk about structural models and machine learning models, we will say the same phenomenon. And again, this is just explaining what I said in the previous slide. If you have the slides this way, people can follow along without this sort of lecture. So second, so I've talked about reduced form models, and reduced form models have made a fairly good baseline for forecasting performance and sort of the improvement due to this pooling method. So now I'm going to talk about structural models. The main structural model I use is the Smets-Wouters 2007 DSGE model. And here, again, you can see the performance improvements, right? So I only have one model, but again, we have significance across the board, including a less than 1% significance over the first 3 horizons. Again, this is forecasting the same US GDP test set. Again, the ultimate performance is not as good as reduced form models. Reduced form models are around 2.5 root mean squared error. And again, so you may take this improvement of 25% a little bit with a grain of salt because it's coming from a much higher level. And so it's, of course, forecasting improvements are easier to obtain when your baseline forecaster is poor. But again, the structural models aren't used as much for forecasting. They're all often used partially for policy analysis. And this illustrates a relatively costless way to improve the external validity of your structural models by just using a pooled data instead of just US data, right? And so that's the main takeaway here. The main takeaway is not really to use this Smets-Wouters DSGE model. In this case, if you estimate in a Bayesian fashion, you actually get improved performance. We choose not to do that because all our other models are sort of estimated via maximum likelihood or some other frequentist approach, and so it's easier to compare. However, if you are sort of estimating DSGE models, you might not be doing it for forecasting, but if you want to do it for policy analysis, using pooled country data is a easy and almost costless way to improve the external validity of your models, right? And here you see the improvement across the board, significance across the board. The improvement is, I think, on average 25% of the baseline root mean squared error across all horizons, right? So like huge improvements in root mean squared error, and this is an easy way without changing the equations of your model, without sort of any sort of complicated mathematical proof or improving the optimization procedure. It's an easy way to improve the external validity of structural models just by using pooled data. This is again says exactly what I just said for people that are sort of have the slides and are not listening to my presentation. I have what I'm saying so they can follow along. Again, this is actually the out of sample, so this is the sort of analog to this graph right here, but for our structural model. The first 2 lines are again the same same 2. This is US only, this is world data, and this is world data out of sample, right? And as you'll notice, the world data out of sample actually outperforms world data. So when you take out the US, it actually improves performance. And one of the reasons we thought this might be the case was we thought that parameters actually might be more stable across space. So for example, US data in 2020, the deep parameters are more similar to French deep parameters in 2019 than they are to US parameters in 1970, for instance, right? And so this is actually the second complaint that we're trying to address, and we didn't spend a ton of time addressing this complaint, but the second complaint comes from, Parisian and some other, forecasting people, where you say if you pool across countries, right, the parameters are no longer actually have an interpretation of being sort of a country parameter. They're actually the average parameter across countries, right? And this leads to sort of more murky interpretations of your DSG model. However, this graph sort of shows, and it's only suggestive, it's not like super, super definitive, but this graph sort of shows that essentially that perhaps parameters are actually more stable across space. So again, like French parameters are more similar to US parameters in 2020 than the US parameters are similar to themselves across time, right? And this kind of makes sense. Like, the economy has globalized a lot, and I think most developed countries are fairly similar. And most developed countries like France and Germany are more similar to the US now than the US was to itself in the 1960s. Like, there's everyone is more into services. There's no less manufacturing in these countries, whereas in the 1960s, there was a manufacturing-driven, savings-driven economy for the U.S., right? And this sort of provides suggestions when we take out the U.S., because the U.S. is the only country in this sample that really has data that extends all the way back to the 70s, 80s, 70s, and 60s. And so when we take back this data, we actually get improved performance, right? And so we wanted to test this out a little bit more with the second test. And the second test is less conclusive, but still somewhat persuasive. So what we did here is this test the sort of stability across time and across space. And again, it does seem like, across time, that would be the, so the world data would be across time, right? That's all countries across all periods in time. The 1995 plus data is all the data except for we take any data after 1995, no data before 1995. And as you can see, the data across time does roughly as well as the data that includes both time and space, right? Which sort of suggests, I think it does slightly better on average, root mean squared error wise, using only 1995 plus data as opposed to the whole data set, which includes data pre-1995. This suggests that maybe the data pre-1995 is not, the parameters are not as stable, right? They're not as predictive for, our test set, which is 2008 to 2020. And again, you do have that trade-off, right? So again, you may argue, or some of the forecasting literature does sort of argue that if you use data across space and pool it, you get a mean parameter rather than an actual parameter. But we would argue that even across time, that parameter is even less stable, and even if it's not a mean parameter, there's still some sort of averaging going on across time, because across time the parameters doesn't seem to be almost as parameter stability across space seems to be as stable, if not more stable, in terms of predictive power than parameters across time, right? And this chart sort of illustrates that. At least you can say, if you go across space, you can use less time dimension, right? You can go back less far in time, and this chart sort of shows that if you go back at state, at a minimum, you are not going to do any worse. You may not do much better, but at a minimum, you're not going to do any worse by looking at parameters across space and estimating your model using a pooled method rather than using more data but going further back in time, right? And this sort of illustrates that, and that's the sort of second critique of why you should not use pooled data for macroeconomic methods. Again, these two slides is not like definitive research, but it's just sort of somewhat suggestive that this second critique, which is the sort of the mean parameter and parameter stability, may not be valid, because regardless of whether you go across time or across space, you're always going to deal with lots of parameter instability. Or the same amount of parameter instability. Whether you think it's a lot or a little, I guess, is up to your interpretation. Yeah, and then again, this is also, sort of discussing this chart. The results are sort of inconclusive, but you cannot say in any definitive way that they're worse, right? Across space, the parameters have more predictive power, actually, slightly more, but definitely not significantly more, but slightly more predictive power across space than parameters do across time and space, right? And so the second thing we will talk about, so the last thing we'll talk about is machine learning models, and the first machine learning model I'll talk about is the recurrent neural network. And so again, sort of our story, going back to our story, initially is we have these sort of reduced form models, and these reduced form models had somewhere between 10 to 20 parameters. Our structural model had around 40 to 50 parameters. And so, we're seeing improvements across root mean squared error as we increase the complexity of our models. And so the natural extension to this is, why not use a super nonparametric model and test the sort of outperformance of these nonparametric models? We will use two approaches, a recurrent neural network approach and an AutoML approach. The first one I'm going to talk about is a recurrent neural network approach, because that is actually a single model. The AutoML approach is an algorithm that takes the data and learns and runs a horse race of 20 or 30 different machine learning models and reports a sort of best machine learning model. And again, we do this obviously on a validation set and then finally on a test set. But again, this RNN also demonstrates a sort of outperformance of a non-parametric machine learning models, right? And so before I actually discuss the machine learning models, I'm going to just describe what a recurrent neural network is. A recurrent neural network is basically another name for a state space model. All recurrent neural networks are state space models. They just have more bells and whistles than the state space models that economists are typically used to seeing. Like a linear state space model, the RNN will have latent states similar to the below representation and a measurement equation. So you have a state transition equation and a measurement equation. The main innovation of the RNN is to use gates, a logistic regression that is element-wise multiplied to the states. This sounds confusing right now, but I will explain this in the next slide. What the gate allows you to do is essentially the gate is learning a number between 0 and 1, and so if the state starts to explode, it will learn a value close to 0, and so it can constrain the state from exploding, and you don't need to do any sort of filtering to keep the state from exploding. The model will learn via its own dynamics how to prevent the state from exploding by essentially learning values of gates, gate values that are close to 0 when the state starts to become large. So here is the gated recurrent unit, which is the recurrent neural network we use. These four equations are essentially the make up the state transition set of equations, and this is sort of the analog to the measurement equation. So I'll explain these equations in some depth, not too much depth, but a little bit of depth. So ZT is a function of the xt, which is your inputs, ht, which is your previous state, and bz, which is your, it's the constant term in your regression, right? And this sigma is just a link function. It just means that zt is a logistic regression. Zt is a number between 0 and 1. Rt has the same thing. It's a number between 0 and 1. Not hugely important. Again, it takes the same inputs. It just has different parameters. And here is the gate. Here is the first gate, right? What happens is Rt is element-wise multiplied times ht minus 1, right? And so what happens is if the state starts to go off to infinity, Rt will learn a number very close to 0, and when this gets element-wise multiplied, this input no longer explodes. It is now constrained to be stationary, and this h hat of t is now constrained to be stationary as well. This sigma is just another link function. It's actually a hyperbolic tangent link function. It's not super important exactly what it is, but this constrains h hat of t to be between -1 and 1 instead of 0 and 1. And so this Rt prevents ht minus 1 from getting too large, right? And again, because Rt is a function of ht minus 1, if ht minus 1 is large, this u will learn a negative value, and this will, u will have negative coefficients, and this Rt will be, closer to 0, right? And likewise, Zt also does the same sort of thing. It's another gate. You can think of this as sort of a weighted average. So, because ZT is a number between 0 and 1, you have, it's a sort of weighted average element-wise multiplied by the state at time t minus 1 times h hat of t, which is sort of the first draft of today's state, and you're just taking an element-wise, you're just taking a weighted average of the two, and again, if h hat of t is too large, starts to blow up, then this z will learn a small small number close to 0. If ht minus 1 is a more accurate picture of the state today, then this z will learn a number again and learn a number close to 0, right? Or it will learn a high number if ht minus 1 is not very relevant to understanding ht, and x of t is more relevant, for example, in understanding ht. So this is how the state transitions, right? You have these four equations, and this governs how ht minus 1 becomes ht. Once you know that, you can just, it's a neural network, so you can add, additional bells and whistles. You can, recursively add, you can add a link function here. You can recursively add, the output of the first layer can be the input to a second layer, and so on. But in this most simplest form, you just get a normal linear measurement equation, right? You take ht, you take the inputs, and it gives you the outputs, right? And here in our machine learning, in our GDP forecasting situation, yt and xt are basically the same variables, right? We're forecasting GDP, and the inputs are GDP consumption and unemployment, essentially, right? And so this sort of explains what is going on in a GRU cell, or a gated recurrent unit cell. Here is the architecture of our model. Again, we use what are called skip connections. We have batch normalization. We use the GRU right here. And so this is the sort of model architecture. It's not super important for people that don't really have a background in neural networks, but I feel like if you had some experience in deep learning, you could sort of understand what our architecture is kind of doing. Skip connection, skip connection, skip connection, batch norm, batch norm, batch norm, batch norm, and before we actually put our model into the gated recurrent unit, we actually add dense layers to actually project the input into a higher dimensional space. This leads to easier optimization for the recurrent neural network, as well as allowing the recurrent neural network to work in a high dimensional space that the neural network is comfortable with, because this projection does that for it. And the whole thing, of course, is trained end to end. And so the forecasting improvement for the RNN, so I explained it, and again, there is huge forecasting improvement. As you can see, the forecasting performance is only 23% versus, I think, 25% for the structural model. But again, as you can see, the structural model actually, their final performance was worse, right? So the initial baseline level of performance for the RNN using only US data was better than the DSGE model when only using US data. So even if the percentage root mean squared error improvement is less, I still think the improvement is more significant and more powerful, because it started from a better baseline and the US model had more predictive power than the structural model. And again, I think this level is state of the art compared to the reduced form in the structural model, and these numbers are all fairly state of the art. If you compare this to the factor model does really well, 1 horizon and 2 horizon head. I don't think it beats the factor model, but other than that, at long horizons it beats the factor model and every other model. But at short horizons it beats all the models I've shown already, whether they're trained on US data or world data. Again, we have significance on the shorter horizons especially, but even in horizon 4. And again, it's the same chart. And so I showed you the improvement with the recurrent neural network model. I will now show you the AutoML model and sort of some other stuff added in at the end. So again, the AutoML model, there is no actual model here. Basically, the AutoML model is not a model, it's an algorithm that takes a horse race of 20 or 30 different models, runs them all, evaluates them all on the validation set, and then once they're evaluated on the validation set, it sends them off to the test set, and I test, and this is the sort of test set performance of these AutoML models. As you can see here, this performance again, the performance here is something like 12% root mean squared error. You have some decline in performance here. But overall, you have something like 10 to 12% improvement in performance. But again, the baseline AutoML model is very good, right? And again, keep in mind, when using US data and using world data, the model that is being chosen at each horizon is not the same, right? So this is probably XGBoost, and this might be a deep learning method, right? So it's not actually an apples-to-apples comparison. You just do get models that are less data hungry, that are that end up becoming the winner of the horse race in the AutoML model when only using US data, and then models that are more data hungry when you have a larger data set, right? And so this improvement is not an improvement of a single model, which is why it's not really comparable to this chart or all the other analogous charts and all the other charts. But as you can see here, the model does, it has a root mean squared error below 2, which is far better than any of the models tested, including the factor model, which I'll show you and stuff like that in the next couple slides. Likewise, all these performances are almost, I think all these performances except H4 is state-of-the-art, even though actually H4 with US data is like state-of-the-art, but the reduced performance that comes from world data actually makes it not state-of-the-art compared to all our other models, I guess. I don't want to say state-of-the-art, but compared to all our other baseline models, each one of these world data models outperforms all other models except for maybe the RNN at H5, but that's one of our models as well. And so here is the chart that shows the outperformance. The bolded colors indicate if our RNN model or AutoML model is better than all the baselines. And as you can see, along each horizon from 1 quarter ahead to 5 quarters ahead, our machine learning models, either the RNN model or the RNN or the AutoML model, is better than any of the is better than any of the baseline models, right? So the VAR4 US and world by itself, AR2 US and world by itself, SMETS-Voucher is only using US data. So this doesn't actually use our structural model section. This actually uses the original SMETS-Voucher's parameters, because those have actually better performance than our structural models. And I discussed a little bit about that why in that section. And then the factor model, again, only uses US data. And the reason, of course, is essentially that it's hard to get data on 248 covariates for other countries, simply because the data typically isn't there, or is that very hard to hunt down. And so this only has US data, but again, we outperform all baselines, including baselines that use world data. This US data, SMETS-Voucher's, outperforms the SMETS-Voucher's world data that we have in our structural model section. And I think the other thing to realize is actually we are fairly close to the SPF, right? We're only at 1 quarter ahead, we're only 0.1 root mean squared error points away from the SPF median. This is actually very impressive, because our AutoML, keep in mind, only takes in 3 covariates. It takes in unemployment, GDP, and consumption, and uses it to forecast GDP. The SPF uses hundreds of different variables, also uses real-time variables, and we are, probably, I haven't checked, but we are probably not statistically significantly different from the SPF at 1 quarter ahead. And this is, this is where the, forecasting agencies have the most advantage. This is where humans have the most advantage, and where real-time data has the most advantage, right? And again, you can also see that among our US data models, the only model that outperforms all other models is this Q4 AutoML on US, right? This outperforms all other models. However, it's interesting when you compare our US model with other models US only data, so you remove the world data. Also, we don't outperform, right? So the factor model is better than our AutoML model using only US data. Likewise, the VAR4 is better than our AutoML model using only US data. Here's the same thing. It's only when we move to world data that the AutoML gets relatively and comparatively better than these models, because it is more nonparametric, and it starts to just sort of run the table in this horse race, essentially. I don't know if that makes sense. And so, you do see relative improvements in these nonparametric models that improve more than the relative improvements of these sort of more linear, smaller parameter models, in GDP forecasting. And so the last chart I have is basically illustrating just the performance of our models in a sort of graph. So this is the graph of the test set, so 2008 Q4 to 2020 Q1. And essentially the blue line is the real data. The red line is our recurrent neural network, the GRU. And then the green line is our AutoML. And as you can see, both our recurrent neural network and our AutoML do sort of forecast a slight recession when that recession happens. And both of them also do sort of do a pretty good job in fitting the expansion period, and even the AutoML actually does a pretty good job getting the sort of ups and downs of the GDP report over the expansion. And you can see both the AutoML, which is the H2O, and the GRU do a fairly good job of being relatively unbiased during the expansion period. Whereas the other models, you can see the DSGE, the AR2, and the factor actually are more biased to the upside, right? And this causes issues when you have this Great Recession. But seeing all this, you have this, and then you have these are the performance of the models, and you have, in conclusion, I showed how you can improve the external validity of a wide variety of models at little cost. I demonstrate increased policy invariance brought about by using a panel of countries rather than a single country. And I showed how this panel data improves the forecasting performance of a wide variety of nonparametric machine learning models, allowing them to outperform all traditional baselines that were augmented with panel data, or pooled or not, right? And this ends my presentation. Thank you very much.